As promised in previous video, now we will describe a more general type of rotational motion, where the rotational radius is not necessarily constant. The distinction from geometric radius is most obvious when the system dynamics causes change of rotational radius. This involves radial motion which doesn't exist in a purely circular trajectory. It can be seen in non-circular motions, like elliptical orbit and spiral motion. Let's first recall that 1 radian is the angle subtended at the center of a circle by an arc that is equal in length to the radius. Thus rotational radius equals tangential velocity divided by angular velocity. It's also equal to tangential displacement divided by angular displacement. To be consistent with the equation, rotational radius should have the unit of meter per radian. The table here shows the comparison between tangential and angular quantities. Note that both of them describe the same rotational system, only viewed from different perspectives. They don't contribute to the change of rotational radius. Changing of rotational radius is described by another set of quantities, which is called radial quantities. Let's derive their units, just like how we have derived the other types of quantities. For the symbols, we'll just use the same letters as the tangential types, but add subscripted letter r to indicate radial quantities. Note that for inertia, the letter I is used instead of m to distinguish it from purely mass parameter. The anchor quantities can be written first, because they are the same for all types of motion. They are period and energy. The derivation formulas connect these anchor quantities to the others. Radial displacement refers to change of rotational radius, thus they must have the same unit, which is meter per radian as derived earlier. Radial velocity and acceleration are just first and second time derivative of radial displacement, which yield meter per radian per second and meter per radian per second square, respectively. Power is the time derivative of work, with standard unit in joule per second. Let's derive the rest of them, starting from the bottom, which is easier. Radial stiffness is unit of potential energy divided by radial displacement squared, which yield joule radian square per meter square. Radial force is work divided by radial displacement, which yield joule radian per meter. Radial momentum is integral of radial force with respect of time, which yield joule second radian per meter. Radial inertia is radial force divided by radial acceleration, which yield joule second square radian square per meter square. Just like for angular quantities, let's compare the derived radial quantities with the original tangential quantities with related by appropriate conversion factors. It turns out that the conversion factors are very similar to angular quantities, but the rotational radius is replaced by angular displacement. Converting linear motion into rotational motion can be done by applying a force perpendicular to the direction of motion. In a circular motion, this perpendicular or orthogonal force has a constant magnitude and is always directed to the axis or center of rotation, which makes it called centripetal force. We see that in circular motion, the rotational radius doesn't change, which means the radial acceleration is zero. But the centripetal force in that system is not zero, which means that there is another force counterbalancing it. This force is the orthogonal force whose direction is perpendicular to the direction of motion. Note that the radial quantities are viewed from the perspective of the rotating system, instead of the inertial system. Now we have another type of motion called orthogonal. So let's derive their quantities like what we did for the other types of motion. Period is the same as in the other motion types. But since the force is always perpendicular to the motion, the work and energy must be zero. That's why we need alternative route for derivation of the other quantities. The orthogonal force is the force needed to keep the rotational radius constant while the system is rotating. It's equal to mass times tangential velocity times angular velocity. This force equals centripetal force in circular motions. Tangential velocity times angular velocity equals orthogonal acceleration. Next, orthogonal momentum and velocity can be derived as integral of orthogonal force and acceleration with respect to time. Orthogonal displacement can be derived as integral of orthogonal velocity with respect to time. Orthogonal inertia is orthogonal force divided by orthogonal acceleration. while orthogonal stiffness is 2 times potential energy divided by square of orthogonal displacement, which is 0 in this case. Let's compare the orthogonal quantities to tangential and angular quantities by their conversion factors. Let's compare the orthogonal quantities to both angular and radial quantities by their conversion factors. In the next video, we will describe the applications of these new rotational quantities in generalized rotational motions. Stay tuned. Don't forget to like and share this video. Also subscribe to this channel if you like to see more contents like this.